Look closely at the things around you: a gold ring, the copper wiring inside your walls, a plastic bottle, or a piece of charcoal. These objects look and feel completely different, but they are all governed by the same set of chemical rules. Every object on Earth is built from elements, pure substances that cannot be broken down any further. Scientists have identified 118 of them, and if you look at the periodic table, you will see these elements divide into two major families: metals and nonmetals. We interact with both families every day, but to see what separates them, we have to test them against physical force, against extreme heat, and raw electricity. Understanding the materials that build our world means learning the opposing rules that dictate their behavior. Physical testing shows the first major difference. When you strike a metal like gold with a hammer, it flattens into a thin sheet. This is malleability. Do the same to a nonmetal like sulfur, and it shatters into dust. Stretching them provides a similar result. Metals possess ductility, allowing them to be pulled into long, continuous wires. Nonmetals are brittle and break under the same tension. Metals also have luster, which gives them their shiny appearance, and they are excellent conductors. Electrons flow freely through a metallic wire to light a bulb. When that electrical current hits a nonmetal insulator, like rubber, it stops. You might assume this means all metals are incredibly hard, but nature often has exceptions. Take sodium. It is a metal, yet it is soft enough that you can take a standard butter knife and slice right through it. These physical traits are only surface-level clues. The primary difference between these two families is their chemical behavior. Exposing elements to fire and oxygen reveals their chemical identity. When elements burn, they combine with oxygen to form new compounds called oxides. If you burn a metal like iron, it sparks aggressively as it forms a new compound, iron oxide. Put a nonmetal like sulfur to the flame, and it burns with a vibrant blue flame to create sulfur dioxide. The real test happens when you dissolve these oxides in water and use litmus paper to measure the result. Dip it in the metal oxide solution, and it turns red paper blue. Dip it in the nonmetal solution, and it turns blue paper red. This color shift identifies a specific rule. Metal oxides are basic, while nonmetal oxides are acidic. These chemical reactions dictate how materials survive in the environment, and for iron, it leads to one of the most common forms of structural damage. Metals slowly degrade through a process called corrosion. For iron, this is rusting, a reaction that weakens bridges, vehicles, and buildings. This damage leads to billions of dollars in repair costs every single year. Rust is iron oxide, but iron doesn't rust just from contact with air. The reaction requires both oxygen and water to be present simultaneously. We can see this in a simple experiment using 3 test tubes, each holding a clean iron nail. Tube A contains dry air, while tube B contains boiled water to remove oxygen, sealed with a layer of oil. Because we isolated the elements, blocking either water or oxygen, these nails remain intact. Tube C is open to both air and water. With both ingredients present, the chemical reaction takes hold and a flaky brown crust consumes the iron. We prevent this by using paint barriers or galvanizing steel with a protective zinc layer. But some solutions are ancient. The iron pillar of Delhi was forged over 1,600 years ago. Its unique composition has allowed it to stand outdoors almost entirely free of rust. Understanding a metal's chemical weakness is the only way we can protect it and ensure our structures last for centuries. In every engineering project, the scientific properties of the elements dictate our choices. We use conductive copper for the power grid and lightweight, malleable aluminum for aviation. We also rely on nonmetals to wrap those copper wires in thick rubber and plastic insulators because they block electricity, keeping us safe from the current. For thousands of years, humans have used heat and force to manipulate these physical properties into tools and machinery. The modern world, from smartphones to skyscrapers, is built on our ability to combine the opposing properties of metals and nonmetals in a single design.